record. Okay, and then once you've done that, try and think about what should, when I show you the polls, what should it look like, right? Like what should the distribution be? What's the probability that you get 0 heads? What's the probability you get 1 head, 2 heads, 3 heads, so on and so forth? Okay. Well, that's just it, right? So like, let's figure it out. Let's try and work out how many possibilities there will be for each. And again, it's a fair coin, right? We'll assume that none of you have a rigged coin on you. And then if enough of us do this, right? There's like 70 of us in the class right now. If enough of us do this, we should start to approach what we expect to be the right number. You're right. There's no right or wrong answer. It's just go and you do it. Dowd, yeah, exactly. Yep, that's it. And we'll go through that too as well for anyone who doesn't see that that's the answer. Okay, I'm going to close it in like 30 seconds here. Well, it should either be 1 or 2, right? The probability of 1 head and the probability of 2 heads are approximately equal. And they're both, 3/8, which is what, 32.5% roundabouts, right? And then 1/8 is about 12.5%. Or is it 37? What is it? 37.5? 37.5, right? Is 3/8? Yeah, 37.5.
1.5, yeah, 37.5.
Will we do the normal distribution? No, that's continuous. Okay, I'm closing her down and share results. Okay, so again, let's think about what we should have. So even if you don't know how to do the calculations yet, we'll do them in a second, but we expect, based off of what the class has said, that A and D should both be about what, 12.5%, right? And then B and C should both be about 37.5%, right? That's what we expect. Okay, so we said A and D, yeah, look at that. A and D should be about 12.5%. B and C should be about 37.5. That's pretty darn close, right? And you all did that experiment, right? Like there was no rigging of this going on. It's not like I did the experiment. Each and every single one of you did this experiment once, and we just tallied what all of the answer should be, right? And this is what we got. We got 37. We got roughly what it should be, modulo, a little bit of noise. But if we did this even more and more and more, we had like 200 people in this class, we'd get even closer to this distribution, right? So let's very quickly talk about how we would get this. The fact that, in case you're not certain, like, why is it 1 and 8? Why is it 3 and 8? Let's just very quickly talk about that. I feel like I would have done one of these in the videos, but maybe I didn't do this exact one. So without doing any calculation whatsoever, how many possible outcomes are there if you flip a coin 3 times? Exactly, yeah, 2 to the 3 is equal to 8. Perfect, good job, everyone. 2 to the 3 equals 8 possible outcomes. Outcomes to flipping the coin, right? And why is that? Because basically we're going to write everything as like heads, tails, heads, right? So this says, if I flip a coin 3 times, the first flip was heads, then it was tails, then it was heads. So you've got these 3 baskets, and then there's 2 things that you can put in the first basket. There's 2 things you can put in the second basket, and 2 things in the third basket, right? So you have 2 options for each of them. You have 3 possible options. So as you all said, this gives you 2 times 2 times 2 equals 2 to the 3 equals 8 options, right? And if you want to, you can actually write them all down. But maybe there aren't that many. We could just write them all down, right? So you get like tails, 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 heads, tails, heads, tails, tails, heads, 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 tails, tails, heads, tails, heads, 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 tails, heads, heads, heads. Is that 8? 1, 2, 3, 4, 5, 6. That's 8, right? And if you wanted to do this just naively, right, without kind of doing any counting sorts of arguments, you could say, okay, well, how many of them have no heads whatsoever? Well, this is the no heads. Maybe let me use colors, make it a little bit obvious, right? So no heads. So there's 1 out of 8 possible options, right? The dice are all fair, so this is an equiprobable experiment. So the probability of any one of these events is all equal. They're all 1 in 8. So how many ways are there to get no heads? Well, there's 1 in 8 probability, right? Okay, 1 heads. Let's go through and try and find them. So there's 1 heads, there's 1 heads, there's 1 heads, and am I missing? No, that's it. So there's 3, and each of them has a probability of 1/8, right? So that gives us 3/8 for 1 head, right? And then if we were to do 2 heads, we get 3/8 as well. And then if we did 3 heads, that would give me just 1/8. Okay, so does everyone see that? Does that work out? Right? Okay. Okay, cool. So this next one is a 2-parter. Let's see. So we're not going to do this one. We're going to do this one. Okay. So all I want you to do right now, just completely and totally guess what you think the answer is. So there are currently, I think, 71 or 72 students in this class. Why do we multiply it by 1/8 again? It was because the probability of any event was 1/8, and there were 3 events that satisfied it. Yeah, exactly. Okay. So there's currently 70 people in this class. There's 365 days in the year. And I want you to tell me, what is the probability that 2 people have the same birthday?
I always like this one.
Yeah, maybe. Brandon, don't say anything. Okay, it's just a total guess. I don't want you to compute anything. I just want you to guess. And by the way, this one does have a correct answer. Yeah, there's, I think, so there's 74 people in the Zoom lecture. I'm here twice because my Surface is in here and Aziz is in here. So I think there's 71 people. There's 71 students. There's 73 people. But let's just do students, okay? So we won't make Aziz and myself indicate our birthdays. So out of these 71 students, what is the probability that 2 of you have the same birthday? Okay, so I'm going to do 30 more seconds. So about most of the class is answered. And again, there is a correct answer to this, right? Probabilistically, I know what the probability is. And I will tell you what it is in a second. All right, last couple of seconds. If you're going to make a guess, get her in.
The first time I looked at this, I was shocked. So
yeah. Okay. So nobody say anything. Majority of the class thinks that it's about, right, okay, so it's, yeah, 71 choose 2, turns out that's an interesting way, Connie, but it's not quite the right thing, because the problem is that it's not just, that would just be the number of ways of picking 2 people from the class, but then you also have to figure out what's the probability that their birthdays overlap. So this computation is not easy. It's not hard, but it's not easy. There's a little bit, no, it ends up being quite a fair bit worse than that, Connie. I'll show it to you one day. Okay, I probably won't do it today because today we kind of just want to get warmed up with birthdays. So the majority of the class said between 0 and 25%, right? All right, let's do an experiment. Let's find out. Okay, so everyone, this is the year, okay? On the left-hand side, here, I'm gonna annotate, okay? So, you know, the left-hand side, these are the months, right? So the first row is January, then February, March, April, May, June, July, August, September, October, November, December. And then you have the days like this, right? You all should be able to annotate and indicate just with something, you know, you can put a little stamp or something here. You should be able to indicate where your birthday is. So you should be able to see, I think under view options on your screen, you'll see something that says annotate, and you can then draw on my screen. Okay, can somebody help Chan here? Because I can't see your guys's, like what you see from your viewpoint, because what I can see as the host is very different.
If you look at the top of the screen, right, it's the little green bar, and beside that green area, you would see view options. If you
Perfect.
click on that, you would go down, and the third one would be annotate.
Perfect, awesome. Okay, so everyone get your birthdays in here.
I think there's an overlap on March 25th. Looks like there's two.
I agree.
I think that's an overlap.
I think there is two. December 21st, yeah. Oh, maybe somebody just got rid of the December 21st mark. Oh yeah, there it is. There's another December. Is anyone today? What day is it? November 23rd. So far, nobody today. Oh, it looks like November 17th has an overlap.
Got two.
Looks like
I don't see anyone with my birthday. So I'm kind of disappointed.
Yeah, it looks like April 5th has one too. Somebody's making a little mark there. I think also April 1st has an overlap. I think two people marked that.
No, it's April 4th that has the overlap.
Yeah, but I think the first does as well. Look at it closely. There's an X under it.
I see what you're saying.
Yeah. Okay. Oh, Chad with, yeah, so you're putting on April 4th. June 8th, we said has one as well, or I don't see one under June 8th. Or Danielle, or is that you telling us and you want us to put it in? Because I'll put it in for you if you want. Okay, so point, there are actually a lot of overlaps, right? Okay, let's see if we can find them all. So there's definitely one here, right?
Yeah.
That's an overlap. There's an overlap here, here. Where else? There's an overlap here. There's an overlap here. Do we see any others?
I think that's mainly it.
I think that's it. Okay, so class, the majority of the class thought that the probability that two people shared a birthday. Oh, okay. So Daniel, so what did you say? November or June 8th? Here, we can, somebody mark June 8th for Daniel.
I did.
Okay, perfect. Thank you. So the majority of you thought that the probability was 25%. And not only was the probability 25%, but it turns out there were at least 5 overlaps, right? So in fact, there are 10 people in the class that share a birthday. So the actual probability, if you do the math, in a class of 71 people, the probability that 2 people share a birthday is 99.9%. It was almost a guaranteed. That is, if I took 1,000 classes, if I did this with 1,000 classes consisting of 71 people, one of those 1,000 classes might have 2 people that don't have the same birthday.
Yeah, it's insane. A lot of people, I would assume they just did 71 divided by 365 and got 19%. So they picked the 0 to 25 option.
Mm-hmm.
But be surprised it's actually not like that at all.
It's actually, yeah, and it's really, the number is surprisingly quite big, right? Exactly. This is called the birthday problem or the birthday paradox. We can talk about it a little bit later if you want, but it's a little bit complicated. So I want us to get a little bit more comfortable with probability before we talk about it. Nice, cool, yeah. Yeah, exactly, yeah. And so you can check it out. It's like once somebody tells you how to think about the problem, it doesn't become too hard. But so again, that's something that maybe we'll talk about on Thursday, depending on how we feel. But yeah, the answer is 99.9%. It's extremely high. In fact, when is it 50? It's at like 30 people, it becomes 50%?
23, I think.
23, yeah. If there are 23 people in your class, there is a 50-50 chance that 2 people have the same birthday, right? It is a coin flip whether 2 people in your class of 23 people have the same birthday. Right. So she had 40 students. And so in a 40 student class, it's 90%. So I got a direct message saying, this student happened to attend another class. And in that class, there were only 40 students and they did the same problem. There was still a bunch of overlaps. And yeah, in that case, even with just 40 students, it's still a 90% probability, right? Yeah, it depends on how many people are in the class, right? It depends on how many people are doing this survey, right? Because obviously if there's 2 people, if you have a class of just 2 people, you say, what's the probability that your birthdays overlap? It's very, very unlikely, right? But as you get more and more people, it becomes statistically more and more likely that it happens, to the point where if you have 100 people, yeah, exactly. If you have 100 people, it becomes 99.9999997 or something silly like this, right? Like it's supremely, even just 100 people, it's very likely. So this is a nice and interesting problem. And we'll talk about it a little bit later. I just wanted to show you that this was kind of an interesting thing, right? So we just had a little bit of fun before showing you all, before actually doing some work. Okay, clear everything. And now I'm going to turn off annotations. So you won't be able to draw anymore. And I know that makes you sad, but it is what it is. Okay. All right, so probability can be cool. That being said, I hate stats, whatever, it is what it is. All right, let's do a warm-up question. Now we actually have to do math. So up until this point, we've kind of been doing, some experiments and stuff. We haven't actually had to do any math. It was mostly just guessing. So now we're actually going to have to do some work, and let's see. So hopefully you recognize this from last week, right? We had a very similar problem. And in that problem, it just said, count the number of ways that you can rearrange the letters of the word commerce such that the word meme appeared, right? All together. And so now we're asking, what is the probability that if you randomly shuffled the letters, that would happen? So not just how many ways are there, but if you randomly shuffled the letters, what's the probability that it happens? Okay, 30 seconds. All right, I'm shutting her down right about now. Okay, great. So the majority of the class has said C. By majority, I mean exactly 50% of the people who answered. So majority of the class has said C, and C is absolutely the correct answer, right? So good job, everyone. Let's talk about why it's C in case you didn't get C or misclicked or whatever the case might be. Okay, so this is question, which question is this? This is question 4. Okay, so we have, last time we counted the number of ways that you could arrange the letters of commerce and meme would show up together, right? And remember that when we did that, what do we had? C-O-R-C. And remember, we treated the word meme like it was a single letter, right? So we treated this as a one unit, right? Or one letter. So the number of ways that we could arrange this and keep meme together was 5 factorial divided by 2 factorial, right? So the number of words with meme together is 5 factorial, because that's the way of arranging the 5 individual letters. But we have 2 C's, right? C's are duplicate. And so in order to account for that, we have to divide by 2 factorial. So that was our answer from last week. That was the number of ways of computing the number of words that had meme in it. Now, in order to compute the probability, what we want to do is we want to divide that by the total possible number of ways that we can rearrange the words. So the total number of words possible is what? Eight factorial divided by 2 factorial times 2 factorial times 2 factorial, right? So we have 8 factorial because we have 8 letters. But remember, because for every single one of our repetitions, we have to divide by the number of times it occurs, right? So we have 2 C's, 2 M's, and 2 E's. So that's 2 factorial, 2 factorial, 2 factorial, or if we want, 8 factorial over 2 factorial cubed, right? So therefore the probability, but if there are 3 C's, would we divide by 3 or 3 factorial? We divide by 3 factorial. No, it's a good question, right? So the question is, and it came in as a direct message, if there are 3 C's, do we divide by 3 or 3 factorial? The answer is 3 factorial. Namely, you divide by all the ways that you could arrange those 3 C's, right? And so if you have 3 C's, how many ways can you arrange them? There's 3 factorial ways of doing that. Okay, so I got a direct message. Can you explain the 8 factorial over 2 factorial, 2 factorial, 2 factorial again? Sure. So we have 8 letters, C, comma O, comma M, comma M, comma E, comma R, comma C, comma E. If we could distinguish these letters, then there would be 8 factorial words that we could make. But we can't tell the difference between the 2 C's. We can't, right? So we've got 2 C's here. We've got 2 E's, and we've got 2 M's. That kind of looks the same. Maybe let me put hats on them. And so we have to divide by the number of repetitions of each letter in order to get the correct number of ways. Okay? Because in meme, you're not worried about it. It's true if we were like talking about all the ways that we could rearrange the letters of meme. Like if I just had M-E-M-E, and you were allowed to arrange these however you wanted, you're right. In that case, I would do 4 factorial divided by 2 factorial, 2 factorial. But in this case, there's only one way that you are allowed to put those letters, right? When we're counting them as a single word, it has to occur M-E-M-E. That's just a single block. Like, we're not going to move the words around inside of that. In fact, I think this is like a bonus question that we did after doing this question last week. We said, okay, so now suppose that these 4 letters have to be together, but they don't have to be in this order. And what we ended up doing is exactly what we just said. We would also multiply by 4 factorial divided by 2 factorial squared. We don't have to do that in this case because these have to be in this order. And remember, when the order is determined for you, that means that you don't get to pick the order, and so it actually doesn't affect your calculations. Okay, so does that make sense? Hopefully, everyone. And so to get now the probability, we divide the number of possible outcomes divided by the total number of outcomes, or the number of outcomes that we want divided by the total number of outcomes. So the probability is, so it's the number of outcomes we want, 5 factorial divided by 2 factorial, divided by the total number of possible outcomes, 2 factorial cubed, like that. And you can work that out, whatever it is, 1/84. Okay, so are there any questions about this? Why is it 5 factorial? So up here, why is this 5 factorial? Because we're counting each of these as a different letter, right? So 1, 2, 3, 4, and then all of meme is 5. Right? You're like, I think last week I said, like, pretend it's like the letter X, and then wherever you put the letter X, you would just replace it with M-E-M-E, right? And that's where you would do it. So you're just treating it like a single letter. Okay, everyone's good? Okay, let's do a slightly trickier one. Still just computation, but a little bit trickier. That one's kind of boring. Here we go. Why is it 1/84? I don't know. That's just how it works out. Like, there was nothing kind of special about that. It's just if you actually plug those numbers in, yeah, you just plug those numbers in and that's what you get. If the question is like, is there a slicker way to get 1/84? I don't know of it. Maybe if we thought about it a little bit, we might be able to think of a nicer way of coming up with that answer. But right now, it's just, that's how the numbers worked out. M is that number at the bottom, right? So you have to read all the options, but it says at the bottom where M is this number. And it's just because if we were to actually try and put M in there, it just would have been a nightmare, right? But M is basically the total number of ways that any match could happen. Yeah, Curdy, sorry, it's part of the question. It's not part of D. Yeah. So each one of these, A, B, C, and D, is that number divided by M, where M is that number at the bottom, which has been included separately because it gets a little bit clunky if you include it in the same line.
The people that went to tutorials earlier today might have a little bit of an advantage because there was a very similar question covered in tutorials.
Okay, let's do 30 seconds. Okay, so I'm pretty happy with more or less how this went, even though, as you're going to see, you're going to be like, wait a second, we didn't really reach a majority. So the majority of the class chose A and B with a couple of people in C and D. And A and B are obviously similar. There's just a very small difference between them. So I would kind of take this as being most people thought A or B was right and just wasn't sure whether it was 6 factorial or whether it was 5 factorial. Maybe you were guessing because you saw that M had this particular form. That's a possibility. But let's figure out how we would do this, okay? So the first thing that we want to do is that even though the question tells us the total possible number of all possible matches, it's this number M here. Let's make sure that we understand where that number M comes from because it's going to help us figure out the probability in general, okay? So this is question 6. All right, so let's first, again, let's make sure that we can understand where or why an M was the total number of matches possible. Okay, so let's count the total matches. Possible matches. Okay, and so what we've got 12 people. And so the first thing that we want to do is say, let's determine who the first set of people who are going to face each other is, right? Like, you know, we're in a single round of our chess tournament. We're going to choose 2 people who face off against each other. How do I do this? If I just want to choose those 2 people, how do I do that? 12 choose 2, perfect. So 12 choose 2. This is the first match, right? Okay, how do I choose the second match? Okay, sure. Yeah, 10 choose 2. Exactly. 10 choose 2. So this is the second match, correct? Because there's 10 people left over. And again, I'm going to choose 2 of them. And then the third match, 8 choose 2. And I think we start to see the pattern, right? 8 choose 2. This is the third match. 6 choose 2, 4 choose 2, and then 2 choose 2 at the end, which is just 1, right? So this is the fourth match. This is the fifth match. This is the sixth match. Okay. But now some of you might have noticed that in the answer, we divided by 6 factorial. Can anyone think about why we must have divided by 6 factorial? Why is that important? Repeats of what? So yes, but repeats of what? Like what specifically was there repetition of? Because repeats isn't of particular pairings, or right. Oh, and that's a great way of saying it, because order doesn't matter. Yeah, Edward, yeah. Okay, so Edward, A versus B, this is a great thing you've pointed out, and I really want to hit it. A versus B being the same as B versus A is actually why we chose the combination, is why we chose C and not P, right? So we've actually already accounted for that one, A versus B being the same as B versus A, we accounted for that when we used the C, right? So that actually does already account for that. We're not worrying about elimination yet. That's a slightly more complicated question, but that's an interesting idea. Okay, yeah, here, let me put it another one. I think you all have the right idea, and it's just a matter of articulating it, which can be a little, right, exactly, Chen, that's a great way of thinking about it. Let me put it a slightly different way, though. I think you all kind of have the right idea, but let's nail it down. What if I labeled my tables, right? So they're all playing chess, right? So they've each got, they're sitting at a little table here, and they're going to play chess, right? So this is table 1, and that's this pair. And then here's another table, right? And then here's another table, and so on and so forth. So there's actually 6 tables. So I've determined which 2 people are going to play at table 1, which 2 people are going to play at table 2, which 2 people are going to play at table 3, and so on. But the problem is here is that I've assumed that the order matters, right? I've assumed that if these 2 people play at table 1, that's different than if I chose those 2 people to play at table 4. Does that make sense? Like the table doesn't matter, right? We only asked for the matchups. We don't care what table you play at. The way that we've done this, where we do 12 choose 2 times 10 choose 2 times 8 choose 2, is saying that the order of the matches matters, right? But the orders of the matches doesn't matter. This is just a particular round. You don't care like what the order these people play in. You just want them to face each other and then tell me who wins at the end. Does that make sense? Okay, is anyone confused about that still? It's right, exactly. It's not labeled for this question. Do you remember when we were doing the question about like Ihsan and Aziz sitting in the table? And I said it didn't matter which like chair they sat at. The only thing that mattered is who was beside each other. This is the same sort of thing. We don't care which table these pairs sit at, right? All we're trying to do is figure out who's playing who, and then you can send them out there and be like, go find your own table and play against each other. We're just trying to figure out the total number of possible ways that these people can play each other in a chess match, right? So the table that they're at doesn't matter. If the table did matter, then this would be the correct answer. But because the table doesn't, we have to divide by 6 factorial. So the players playing the first match. No. Okay. So what I'm saying is, so let's do a simpler problem. Let's suppose there are 4 players: player 1, player 2, player 3, and player 4. Okay. So I decide first, this is going to be the match: player 1 versus player 2, and player 3 versus player 4. Okay. So do you all agree that this is the same matchup as player 3 versus player 4 and player 1 versus player 2? Yeah, those are the same matches, right? So what we're saying here is that the order of these matches doesn't matter. It doesn't matter whether I wrote player 1 versus player 2 on the left or player 3 versus player 4 on the rest. And maybe, Agam, that's what you meant. Like, I'm not saying that they also can play the first match or the fourth match. What I'm saying is it doesn't matter what match they are, right? Exactly. So dividing by 6 factorial says that we are accounting for the fact that order doesn't matter. Exactly, right? Because the 6 factorial is saying, what is all the possible ways that I could have just rearranged the 6 tables, right? So the 6 factorials gets rid of that overcounting. Just like here, right? We can see that I would have divided by 2 factorial in this question because there were 2 possible tables. And I'm just saying it doesn't matter which table. So I'm going to divide by all the ways that I could rearrange the tables. Right? What does 5, right? Okay, so this is a good question, Aiden, right? And we're going to get to that. So is everyone okay then? So we divide by 6 factorial. So let me just finish this off and we'll get to the 5 factorial. So divide by 6 factorial to get, that gives us our total answer, right? 12 choose 2, 10 choose 2, 8 choose 2, 6 choose 2, 4 choose 2, 2 choose 2, which is just 1, divided by 6 factorial, okay? So that's the total number of matchups, but, right, and this is gonna answer your question about the 5 factorial. We were specifically told to determine the probability that Beth and Benny face each other, right? So what we've got Beth and Benny, they are at a table, right? They already are matched up. And now what we need to do, what we're trying to do is we're trying to figure out all the possible matchups where Beth and Benny play each other, right? That's what we're trying to do. We're trying to count all the ways that Beth and Benny can play each other and then divide that by the total number of ways that a match could happen. Exactly, they count as one, right? So that is a single matchup, and that's already fixed. So now there's 5 other matches, right? So how do I choose this match? How many ways are there to choose this match? 10 choose 2, right? Because there's 10 people left because Beth and Benny are out. They're already matched up, right? 10 choose 2 for this one. How many for this one? 8 choose 2, exactly, and so on. 4 choose 2, 2 choose 2, okay? But again, I have this issue of saying that order matters here, right? And the question is, do I divide by 6 factorial, divide by 5 factorial? And 6 factorial is A and 5 factorial is B. So now we have to be careful about what we've done, right? What we've computed. So the question is, do we divide by 5 factorial or do we divide by 6 factorial? By percent factorial. Yeah, no problem. Okay, so Ain, you say 5. Davin says 5. Brandon says 6. Okay. Anyone else have an opinion? Okay, Kayla says 6. So here's the thing. So for those of you who said 6 factorial, it's easy to say like, look, here's their table. I can move them around. But the thing is, I actually haven't counted Beth and Benny, right? They're not part of my computation. I'm just saying Beth and Benny are already a match, right? They're guaranteed to match. I didn't account for what table they're at. Do you agree? Right? The fact that when I multiply these, I'm saying that order matters, right? I'm saying that this match is different than this match, right? Beth and Benny have not been included in this calculation, right? They are separate. They have already been decided that they have to play each other. So all I need to do is figure out the number of ways that the other 5 matches can occur, which means I actually want to divide by 5 factorial. Right, exactly. Yeah, I knew what you meant. And there was some like something happened there with the typing, but exactly, they've already been fixed and they were not part of our computation, right? We were just trying to figure out how the other 5 matches happened. And we just needed to make sure that the order of the other 5 matches didn't matter, but we did not include Beth and Benny in our calculation of the other matches, right? Because if we had said that order mattered, what we would have done is said, okay, well, let's suppose they're at the first table. And so there's one option, and then this is the way of doing tables 2 through 6, right? And now let's put them at the second table and do the same thing, right? And then let's put them at the third table and do the same thing. And then I would have added all of these together, right? If Beth and Betty, in what sense? In that we cared, because they are included. It's just that we can't choose them because they have to face each other, right? So it depends on what you mean. If the question is worded so that they didn't have to play each other, if the question is worded so that we worried about which table they played at. But everyone, do you see, if you consider all the ways that Beth and Benny can play at a different table, what this would give you is 6 times 10 choose 2 times 8 choose 2, right? Because there's 6 ways that I can place Beth and Benny at a table. And then you would divide by 6 factorial, but that's exactly the same thing as just taking the original answer and dividing by 5 factorial, right? Right, so the final answer that we get is 10 choose 2 times 8 choose 2 times 6 choose 2 times 4 choose 2 times 2 choose 2 divided by 5 factorial, all divided by 12 choose 2 times 10 choose 2 times ... times 2 choose 2 divided by 6 factorial. Maybe let me put brackets, make this a little bit more. That's the final answer. It's not that they're at a fixed table, Agam, it's that we don't care what table they're at. And we've already said we don't care what table they're at. Like once we've said they have to play together, we've said they don't like, oh, for sure, Brandon, this can be simplified. There's a ton of cancellation here, right? There's a crazy amount of cancellation. But so Agam, we're not saying that they're at a fixed table. We're just saying we don't care. They're already matched up, right? We don't want to care about tables at all. All we want to care about is matches. The thing that I'm saying about tables is that when I write this down, I'm saying that the orders of the matches count. And that would be the same thing as labeling the tables and saying that the tables mattered, right? The problem doesn't have that. It just says matches. I just want to know matches. I don't care where they play. And so the thinking about labeling tables is just to help you think about why order matters in this case and why we want to get rid of it. Okay. In fact, Brandon, it looks like if we did all this cancellation, you'd probably get like 6 over 12 choose 2 or something. Which maybe there's an even easier solution that it just immediately pops out as 6 over 12 choose 2. I'd have to think about it a bit to see why that would be the answer. But I think if you actually do the cancellations, that works out. But to be able to justify why it's that number, other than just that's how the math works out, maybe there's a cooler solution. I'm not 100% certain. This answers full marks.
Oh, yeah. So just quickly, I'm going to hop in and stop my tutorial right now.
Okay, sure. See you later.
See ya.
So is the denominator of the final answer the total number? Right, exactly, Christian. Yeah. This is the total matches. And this is the Beth v. Benny matches. Right, because that's how we determine probability. We say, what are the number of things in the event space that I want divided by the total number of possible outcomes. Okay, so does that make sense? That one's a little bit tricky. That one's a little bit on the answer is B. So this was B, right? So if you look at this and we go back to here, that is B. Yeah. Okay, any other questions about this one? So if it mattered which table Benny and Beth were in, would it be like you just wouldn't divide anymore, right? So Samantha, that's a great question, but it's actually a totally different question. So if it mattered which table they were at, the answer would be 6, 10 choose 2 times 8 choose 2 times 6 choose 2 times 4 choose 2 times 2 choose 2. Okay, so if the table mattered, this is the answer. Why is the possibility B and B matched together by calculating others? I'm not sure what you said there, Connie. What do you mean that the possibility of B and B matched together? Oh, what? Why? No problem, Alan. So B and B here, I assume mean Beth and Benny, right? Not like option B. So, because right. So Connie, here's what I want to say. So let me see if I can come up with an example. What I want to do is let me see if I can think of a good way in this. So loosely, just strictly speaking, the way that you compute probabilities is to determine the total number of events that you find favorable and divide it by the total number of possible events, right? See you, Raphael. right, Connie? So events that you find favorable divided by the total number of events. And when we're computing the probability of Beth and Benny playing against each other, we want to know what are all the possible match scenarios, what are all the possible matches in which Beth and Benny play together. But that includes a bunch of matches in which Beth and Benny don't play together, or includes a bunch of matches where other people are allowed to do other things. Does that make sense? Like I'm seeing, yeah, good. I'm trying to see if I can come up, with kind of like a nicer example. Like using coins or something. But yeah, if that makes sense, I won't worry about it. But yeah, you're just trying to count that number. That's all. Okay. Question. I don't have the tutorial, Shanze, so I don't think I can do it. So if you give me the tutorials, I might. No problem, Connie. See you later. Nice. Okay. Let me see. Oh, and then I just was immediately inundated. Question 2. Consider 5 cards. Hands by convention. Hands are unordered. How many hands contain at most 1 club? Okay. After that, can we do part 2, question 1 in assignment 6? Sure. Okay. So what does at most 1 means? Yeah, I mean, but you got to get used to them, right? Because these are kind of like really nice places for us to take examples. So to have at most 1 means that you either have 0 or you have 1, right? So if this is tutorial 9, Q2, right? So part 1 is how many hands have at most 1 club. Okay. Well, here's the thing. A lot of these, even if you don't play cards, the only thing that you really know, yeah, the club is the leaf sign. The only thing you need to know is the suit names and their ranks, right? But like I said, we tend not to ask card questions on term tests because it kind of, some people aren't familiar with the standard deck, but we'll see. Okay, so if you have at most 1 club, that means that you either have no clubs or 1 club. Does everyone agree? If you have most 1 clubs, you either have 0 clubs or you have 1 club. Okay, so what you can do is you can count the ways that you have no clubs. So if you need to make a 5-card hand and you're not allowed to have any clubs, first of all, how many cards are there in a deck that aren't clubs? Yeah, exactly. So what is that, 39, I think? And you need to choose 5 of them. So what is the answer? Perfect. Okay, now, when I say 1 club, minus 13, so basically they're just saying, yeah, there's 13 clubs, so we just get rid of all the clubs. Or what you could say is there's 3 other suits and each of them have 13 cards. So that means there's 3 times 13 equals 39 cards that aren't clubs. Does that make sense? Yeah. Okay, so when I say 1 club, I mean exactly 1 club. So how many ways are there to choose a club card? How many ways could you choose a club? 13 choose 1, right? Which is the same thing as just 13, right? And then how many, now the other 4 cards cannot be clubs. We said there's 39 of them, right? So how many ways are there of choosing the other 4 cards? Perfect. There you go. You say that the ace and king are consecutive. How many split full houses can be formed? Oh, that's a beautiful question. Okay. So question 2.2, I do want you to spend some time with. This is a fun one. It actually really helps that they made the ace and the king consecutive, right? But very quickly, maybe let's talk about 2, because I suspect that the people who asked this were really more concerned about part 2. So we need to do a full house. So we need a 3 card, 3 of a kind, and 2 of a kind. Oh man, this is dirty. How many ways can you choose the first rank? I love this. Yeah, this is question 2, part 2. How many ways can you choose the first rank? So let's say we're choosing the rank for the 3 of a kind. 13, choose 1. Okay, yeah, so we're going to do the 3 of a kind. So again, that's 13. So this is the 3 of a kind. Okay, now, once you've chosen that rank, how many ways are there to choose the 2 of a kind rank? 12 would be the answer. Right, okay. So 12 would be the answer if we were just looking for the total collection of full houses. But this question is a split full house, right? So it's not, yeah, it can't be adjacent. So it can't be, and you remember we did something like this in the last assignment when we were doing postal codes. So it can't be that number and it can't be numbered to either side. So Curdy, exactly, it has to be 10, right? So 10 for the 2 of a kind. Okay, now, once you have the 3 of a kind rank, how many ways are there to choose the suits of that? Okay, so there are 4 suits, right? Does it work out the same? I guess it does work out the same, but sure, Jack, I would say like 4 choose 3, right? Which I think does work out to 4, but right, but yeah, like your answer is totally correct. Does everyone agree? Because there's 4 suits and you have to choose 3 of them, right? And that works out to 4. And Jack, the reason why your answer 4 is the same thing is because it's the same thing as saying, which suit am I not going to include, right? Because I have 4 suits, I have to pick 3 of them. That's the same as saying, which one am I going to skip? And so you get 4, right? Does a suit and rank always belong together? Well, every card has both a suit and a rank, right? Oh, sure. Yeah. So Jack, yeah, your answer was correct, but maybe for fluky reasons, right? So I got a direct message saying, do suit and rank always belong together? Every card has both a suit and rank, right? For example, you always have like the 8 of diamonds, right? So the 8 is the rank and the diamonds is the suit. So here, what we were doing is we were choosing the rank. Let's say I chose 8, right? The 8s, and then we're going to choose 3 of the suits. So for example, hearts, diamonds, and clubs, or something like that. Okay. Once I've gotten the 2 of a kind part, how many options are there? Like how many ways are there to choose the suits for this? 4 choose 2, perfect, right? Because there's 4 suits. We're going to pick 2 of them. And so this is our answer, 13 times 10 times 4 choose 3 times 4 choose 2. Why the 13? Okay, so the question is, can I repeat why the 13? So there are 13 ranks, right? Ace, 2, 3, ... 10, Jack, Queen, King. So all we're doing is we're choosing of the 3 of a kind that have to occur, which of these numbers do we want them to be? Yeah. And then once we choose one, like let's say we chose 2, the 2 of a kind can't be adjacent. So that gets rid of those ones as well. And that's why the next one is a 10. Okay, is that good? Is everyone's fine with this? No problem. Did this take care of whoever asked this? I don't remember who it was, but was that does that help that? And then, okay, sweet. Now, Brandon, you asked for a question, but somebody asked one before you. Somebody asked, Curdy, did you ask about like assignment 6 or something? Part 2 and 3. Okay, here, let me just, I gotta pull them up. Ooh, oh, and yeah, that's a great question, which is super related to your assignment, right? But we did actually do, I think, that more or less exact question in one of the poll questions from last week, though obviously we didn't use like ace and heart. I think we used like jack and heart or king and heart. Oh, right, because then it makes actually, you're right, it is a difference if you do one or the other. But I thought we did both an and an or, but maybe I'm misremembering. It was or? Okay. So Owen, what I would do is again do the complement, right? So just very quickly, you want a 5-card hand with at least one ace and one heart, right? So you want at least one ace and at least one heart. So the complement of this is no aces or no hearts. Do you agree? So that's the question. Compute this now, right? How many hands have no aces or have no hearts? Does that make it easier? Like a little bit more tractable? You can try and solve this one. No problem. Okay, so assignment 6. Now this is the assignment that is still due, right? So I can't say too much. Right, Brandon. Yeah, you do have to worry about the overlap. Exactly. And so the way to do that is to just think about what is the overlap, right? So that is the critical thing to do. So straight occurs, note that the ace can be used to finish the straight. For example, 7-card hand is a straight, but the hand blah is not a straight. How many 7-card hands from the deck are straights? Okay, I mean, okay, lots of direct messages. Ooh, Gurpratap, I don't like that. No, I wouldn't do it that way. Would I? Okay, wait, hold on. Oh, yeah. Actually, never mind. That's totally fine. Yeah. I mean, I would kind of do it in the opposite direction just for the sake of sanity, but no, that's absolutely correct. Yeah, that should be fine. It's the ones with no smiles and no. Right, Brandon. Right, exactly. And so you have to compute that one. Yeah, no smiles and no props. And so once you compute that, you can subtract it and you get the final answer. Yeah, sorry about that. Yeah, I was just trying to read what you had said, but like once I read it a second time, I knew what you were saying. Okay, so everyone, what I want to do here, I don't want to say too much because I don't want to give too much away, but let's think about how you would compute a straight in a normal deck. Okay, how about that? Because I think that's pretty close, right? If I ask you to compute a straight in a normal deck, then you can adapt that to compute a straight in one of these. Right, Jack, exactly. Okay, so how do we compute a straight in a normal 5-card deck? What's the first thing that we should do? So suits don't matter, right? You don't care about suits. How many cards can start a straight? This is exactly the right question. So how many cards can start a straight? Jack, is that you answering Brandon's question? Let me ask you this. How many ranks can start a straight? It is 5 cards. Yeah, Jack, it is. Is it 10? Yes, it is 10. Does everyone agree? Oh, but Curdy, that's true. There are 13 ranks, but a straight can't start with it like a king, right? Like you can't do king, ace, 2, something like that. So an ace can end a straight and it can begin a straight, but you can't have straights jump over the gap, right? After the ace, there's nothing after the ace. So you can start a straight with an ace all the way up to a 10. Not yet. Let's wait. Okay. So the first, like the lowest straight we could have is and let's just worry about ranks. Okay. Let's not worry about suits. So we could do an ace, 2, 3, 4, 5 straight, right? This is the lowest straight. The highest straight is the 10 jack, queen, king, ace, right? This is the highest straight. Okay. And as Brandon says, what we can do is it's enough to figure out which rank starts the straight, right? Because the moment I say, hey, the rank starts at a 4, you know what ranks the other 4 cards have to be. If it starts at a 4, the next one has to be a 5, then a 6, then a 7, and then an 8, right? You don't get to choose those. So if you know which card starts the straight, you know all the other ranks. And you could have done ended the straight. You could have done was in the middle of the straight. You could have done any of those, but let's do the beginning, right? Which card starts the straight. So you have 10 options for the card that starts the straight. Does everyone agree? All the way from the ace up to the 10. Okay. Once you've chosen that card, the ranks of the other 4 cards are chosen. 40 if we're counting all suits. Yes, yeah, that's true. Yeah, I would kind of break it up, but yes, that is true if you were doing that. So now what I would say is let's count the suits of the question of separately. So now we've chosen the ranks, right? How many ways are there of choosing the suit for the first card? 4, right? Here, let me kind of 1, 2, 3, 4, 5. So there are 10 options for this rank, and then there's only 1 option for the rest, right? And then we say, okay, well, there's 4 ways to choose the suit of this one. How many ways? This is the rank computation. This is the suit computation. How many ways for the, okay. So I got a direct message saying, why are there 10 options? Because a straight can start with anything from an ace to a 10. These are the options to start a straight. And Curdy, you're right, there's 5 cards. So we're just doing the first card now, right? How many? Yeah, exactly, Namir. Exactly. There's 4 ways to choose this suit, 4 ways to choose this suit, 4 ways to choose this suit, and 4 ways to choose this suit. Does everyone agree? Curdy, does that answer your question about the 5 cards? Maybe you were just impatient that I wasn't talking about the suits of the other cards yet. Okay, cool. And so the total is that there's 10 times 4 to the power of 5 straights. Right, the suit doesn't matter in a straight, and that's why it's 4 every single time. And you're right, because we do it for every single card, that's why we actually get 4 to the power of 5. Now there is a trickiness here, and you'll notice that we say this in the assignment. We say the note. For those of you who know about card hands, we usually say that a straight flush is not a straight. Yeah, but Brandon, that's the same thing. Right? Take the 4 out of the 40. And you get 10 times 4 to the 5, right? So if you write 40 as 10 times 4, then 40 times 4 to the 4 is 10 times 4 times 4 to the 4. And then that gives you 10 times 4 to the 5, right? So the other ranks are fixed though, right? If I say this is a 7, this has to be an 8, a 9, a 10, and a jack. Right? So once you specify what the first rank is, the other ones are fixed. That's why there's so few straights, right? Like really, this number is not very big, right? Like what is 4 to the power of 5? So it's 4 times 16 squared. 16 squared is 356. So times 4 is 12, 1420. So 14,200. See, Namir, since order matters, how come we didn't use permutation? Order doesn't matter though. These cards can appear anywhere in your hand, but to be a straight, there has to be a lowest card, right? A straight has a lowest card that starts the run of 5 cards. So we're not saying that the order of where that lowest card occurs matters. All we're saying is that once you've fixed what the lowest card is, the other 4 ranks are fixed. So the question is, why isn't it 10 factorial instead of 10? If we choose 1, then the next time we choose out of 9. No, okay, yeah. So we're just choosing the rank. Okay, so we're going to choose. So for the first card, you can tell me which one of these you want to choose. So the person who direct messaged me, here are your options, 8, 9, 10. Okay, so tell me what you want to be the lowest card of your rank. Okay, ace. Okay, so how many options did you have for that? You just had 10 options, right? So where does the 9 come from? Right, because if we want 10 factorial, it's got to be 10 times 9 times 8 times 7. Once you've picked the first card, where are the other 9 options and then the other 8 options and so on? Right? So, right. Okay, so does that make sense? You're okay? Okay, cool. Because yeah, 10 factorial would be just like, what is the number of ways for me arranging these 10 things? No problem. 10 factorial would be the total number of ways of me arranging that, but for the straight, I just need to choose where I start, right? So for the assignment, because there's only 9 cards that can form a 7-card straight, I shouldn't have said that part out loud. And because there is no suits, it's 9. Maybe I can't confirm the answer either way. But that doesn't seem like a terrible way of thinking about it. Yeah. I mean, the MAT133 deck is not that different than a standard deck, right? We just added a suit and added a rank. So you basically do the exact same math, but you do it with our new deck, right? And same thing, we just did a full house, right? So in fact, I'm not going to do an over full house because I did a full house already, right? So what do you mean if the professor is not counted? Is the professor not counted in what? The professor's totally counted. Well, in this option, we're not using the MAT133 deck, right? We're using our standard deck. So it's right, it's not an option here, right? Because there's no professor. But yeah, in the MAT133 deck, professor could not start a straight either. Right? Because the only card after the professor that could occur is the ace, and then there's nothing else. Yeah. So same sort of thing, right? You're not allowed, the ace is weird because it's both the highest and lowest card, right? It is both a 1 and a 13. But no other card is allowed to do that. You're not allowed to push beyond the ace into 2. So you can't do prof ace, 2, 3, 4. Like you're not allowed to do that, right? You have to stop at the ace. An ace can finish a straight. It can also begin a straight, but you can't go beyond the ace in either direction. Okay. All right, let me take a look at 4-5 because that was asked for. Oh, 4-5 is straights and stuff, right? So Brandon, was it you who asked about 4-5? Can you be more specific? Because we just did a little bit of talking about it. So is there, oh, okay. So you don't need it anymore. Okay. Okay, anyone else? Anything else? Of what, the assignment? All right, did I close that? I should have. Yeah, this is what I was saying, right? Like, because I already did a full house, right? I did a full house. Where did I do a full house? I did a full house here, right? So the over full house is the same. You do the same sort of computation. Mm-hmm. So just repeat the same sort of logic. And again, this is all being recorded. So even if you don't remember what I've said too, once I post the video, you can go up and you can look at what I said. But yeah, you just kind of repeat with the same sort of idea, but now you do it in a bigger deck. Be the same idea as what? I mean, yes, it's very similar. And in fact, right, like I recommend that you do, it is similar. It's not exactly the same, but it is definitely similar. I would recommend that, like, especially for anyone who's having trouble with question one, that you go and you do this, you answer these same questions with a standard deck. What is a flush? What is a straight? What is a full house? And then once you're comfortable with how you got your answer in a standard deck, then go to the MAT133 deck, right? But make sure you can do a standard deck first, just to make your life a little bit easier, to help you understand the problem. No problem. All right, is everybody out of questions? I mean, if we finish early, that's okay. It's not the end of the world. See, Danielle? Yeah, sure, Brandon. I'm not leaving. I assume people had questions. When will test 3 information be posted? Friday. Yeah, I'll post it on Friday, Ariana. Usually that's when it is, right? It's usually the Friday before the test. So a week beforehand. In part because we haven't made the test yet. We're actually going to meet tomorrow, and that's when we're going to make the test, right? Because again, what we don't want, I know that some students have this idea that like I make the tests, right? Because I'm the coordinator for the class. That's certainly not true. All 4 of us get together and we spend like 2 or 3 hours and we figure out what the test is going to be of. And we spend a lot of time like arguing about what the test questions are. But part of that means is that we have to get together and do it. I don't want to post test information until we have an idea about what the test is on our end, right? Even though we know what content will be covered, I don't want to mislead you. One thing that we did do last year, which we haven't done this year yet, for example, is there were a couple of times where one professor was like, I don't think we covered this very well. I don't think we should include it in the test. And so I actually explicitly said this in the test material. I said, let's not do that, right? And if we decide as instructors that we're not going to test something, I think you as students deserve to know that as well, right? But if I post test information, then we decide that we're not going to test something, and then I post a correction about it, well, some students are going to miss that, right? And you might say, how is that even possible? You know, everybody reads the announcements, except of course they don't. Trust me, in a class of 600 people, you'd be surprised at how many people don't read the announcements. And then they're going to come back afterwards and get all upset, like, oh, I didn't know. So it's safer just for everyone. We figure out the test first, we post the information. That's probably more than what you wanted, right? You just wanted the answer of Friday, but I just want to be transparent, like why it is that we do that. And 1 week is, I think, you know, plenty of time for you to start studying and to get an idea. And of course, you know that like this week's material is going to be on there. So if you really wanted to start studying, you really could if you wanted to, right? Kayla, I see your question. Give me a second. Yeah, Brandon, I mean, that's for sure fine, but I suspect that's actually not an issue. Let me just double check quick. Because I think that Thursday might actually be traditionally it's a test, I'm pretty sure. Yeah, Thursday 6 to 7 is a test, Brandon, pretty sure. Right, that's the ZZTBA, right? And every class has that, right? I don't know if you've seen that. Every lecture has that. So, you know, in 133, we have the same thing, right? It's like Friday, whatever, 4 to 6. And that would normally be our test slot. It's the exact same thing for that class, right? It's Thursday, 6 to 7 is your test slot. Yeah. So, I mean, yeah, we're definitely, when you have to write a test, don't come to office hours, right? Like for sure, that doesn't make sense, but it's not a real conflict. Most of the time you'll be able to come. Yeah. No problem. Okay, Kayla, let me answer Ariana's question first because I think I can do it quickly. Will there be another bonus quiz? There actually will not be. And I know we have the same thing every year where students ask us a bunch of these questions. So those bonus quizzes are actually not for you. Those bonus quizzes are actually for me. And that might seem a little bit weird. And again, I'm going to over give you an answer. The reason those bonus quizzes are there is we spent a couple of years saying like, these are the core concepts that we want our students to have. And so what those bonus quizzes do is allow me to measure from 1 year to a next how well students are understanding our teaching and our content, right? So those tests, those bonus quizzes are for you as students to tell me how good of a job we're doing at teaching the course material. And that's why they exist. Now, each of those tests, the financial one and the linear algebra one, each of those takes like 3 or 4 years to make, right? Like they take a long time. We have to interview students. We pay students in order to do it. We have to analyze their data. There's a bunch of stats we have to run. So they're actually quite complicated things to make. So for that reason, we actually don't have any more because those are the 2 that we use. So that, yeah, unfortunately that is it. But 2% I think is a pretty solid little bump to your mark, right? Just for something you could have just hit A on everything if you really wanted to. But yeah, that's the idea there. Something similar to question 2 of the assignment. So we did do something similar last week in the polls. I keep closing the assignment and I should have learned better by now not to do that. So I have to open it again. So how many of those hands have exactly 1 professor and 1 smile? I think we did one like that last week's poll questions. Didn't we? I think so. Which one? At least 1 king. Yeah, so this was poll question 9 from last week, right? Did we do that one? Let me see if I can find a YouTube video. Does anyone know if we did question 9? You can save me a little bit of trouble. We did? Okay, yeah. So it should be there then, right? Let me see if I can find a time link and let me send it. And maybe that will help. So we did it last Thursday, you say? I trust you. Let me just. Oh, I hate hearing my own voice, so I'm just going to mute it. Oh, that's definitely was office hours. Yeah, there we go. So, all right, so here is us doing 3-card hand with, oh no, sorry, that's at least 1 king or at least 1 heart. Sorry, that's actually not the right one. Here we go. Okay, so that is us doing exactly 1 heart and 1 jack. And that is very similar, right, to the assignment question. And then the other one, did we do? And we might not have done the other one, but it is very similar to one of the poll questions as well. Right? Poll question 15 is very similar. Did we do 15? I thought we did do 15. Right. Yeah, one of these is at least and one of these is exactly. But the at least one there is the at least or, and the assignment is the at least and. Right? But look at poll question 15 from last week. Poll question 15 from last week is at least one king and at least one heart, which will really help, right? Because it says, it gives you what the answer is as well. So it'll really help you figure out how we did it. I thought we did it though. Did we not do it? I thought we did. Yeah, so where is it? I'm having trouble finding it in the YouTube thing. All right, cool, Brandon. I trust you to find it. Oh, is this it? I think I found it. 2630. Nice. No, but that's the or, right? I don't think that's the and. All right, so that's poll question 11, not poll question 15. I don't think we did 15. Right, yeah. So yeah, what I would say, but somebody did, who was it? Christian, I think, asked about it. And Christian, I don't know if you're still here, but Christian asked me a question. Where the hell did I put it? No, that was our actual work, right? Divided by 2 factorial. These are actually 0-1 clubs, full house. Did I erase where I talked about? Yeah, no, we're not gonna. No, we can't do it. It's pretty, like, once you do it, it really does give it away. But remember, so here's the thing. Again, somebody asked this. I think it was Christian, and it's basically at least one heart. So if I wanted to take the complement of at least one heart, intersect at least one king, the complement of this is no hearts or no kings. Okay, and that is a big hint, I think. Right? So don't try and compute them by actually computing it directly. Compute it using the complement, because the complement is much nicer. But so how do you compute the complement? What is the complement of at least one heart and at least one king? The complement is no hearts or no kings. And if you can compute that, you will get the answer. Okay, so Kayla, does that help a little bit as maybe like a hint, even though I didn't really do it? No problem. Yes, all right, I agree. The multiple choice, yeah, if you just look at the correct answer from poll choice 15 or poll question 15, you're right. It does actually give a really big hint as to what you need to do. November 18th. Oh no, but we didn't actually do question 15, Curdy. So that like, but if you just look at last week's poll questions, it is question 15. And if you look at the answers, it tells you what the correct answer is. And as was, yeah, exactly. It's on Quarkus. It's under the readings. So if you go to where the readings normally are, you'll see something under it that says polls and then in brackets answers, and they should have links and you can click on it and it will take you there. And yeah, it's a big hint as to what the answer is. Brandon, are you just upset that you computed like the hard way? And now that you see the hint, you're like upset that it could have been. Yeah. Not for nothing at all. I mean, again, you doing it the hard way means you found it yourself, which means you'll never forget how to do it, right? With a big hint, sometimes you actually deprive yourself of that learning opportunity. So it's never for nothing, right? It's the same thing. Like, sometimes students will spoil stuff in the chat, and I say, don't say anything, because you don't want to take that learning opportunity away from your fellow students. There are times when we give the answers, right? And because that is valuable, but there's some times when the struggle is absolutely worthwhile, right? And one of the things that we really try and emphasize in math, and that you're really going to see when you take 102, is you absolutely have to struggle with a question, sometimes for a half an hour, sometimes for an hour, for you to really understand the question and therefore to really understand the math. And that's never a waste, right? That absolutely 100% is always a valuable experience. The problem comes in that you start to say like, oh my God, I don't have an hour to spend on this thing, right? Like I've got a million other classes I got to do. I wish that somebody could give me a hint to push me in the right direction. I totally understand that. But if you want to get good at math, the reality is that sometimes you have to struggle on a question for a really long time and then overcome it yourself. And that is how you develop that little thing that we call mathematical maturity, right? And that is like math maturity is a thing. Do you all know about math maturity? Like this is a real thing. It's like your second puberty. Not everyone gets it though. So your mathematical maturity is when it's really cool though. It's when it happens to you, it's one of the coolest things in the world. When you get your mathematical maturity, everything clicks and math becomes so much easier. It's not to say that math becomes easy, but you just understand how to look at problems now. And every mathematician remembers when they had that aha moment where everything suddenly made sense. And it's a very cool thing, but the only way to get there is through a lot of struggle. Mine was probably halfway through my second year of my undergrad. And I was doing specialist, like third year analysis. And, I was getting by up until that point, but it was a lot of hard work and I didn't really understand how to look at stuff. And just in that class, I understood it and everything made sense. And there was something about that class where I just went, yep, I got it. And then from that moment on, everything was fine. And again, some stuff is still hard. That kind of doesn't change. But yeah, it really changes your perspective and how you view things. And it's a very cool thing when it happens and when it happens, right? It's just, and again, like this isn't special about math. Anyone who's done an instrument or I think anyone who's done a sport knows the same sort of thing where you struggle with something for a long time and then one day you go and do it and you can just do it. And it's this really cool feeling. It's the same thing, but with mathematics, right? So yeah, it's a really cool thing. So for probabilities, we subtract the complement from the total, right, exactly, yeah. So for so what you would do for this case, when you find the complement to get this answer, then without the complement, you would take the total answers minus the complement, right? So exactly, direct messenger. That's how you would do it with the complement. No problem. Okay, anyone else? Anything else? Do you know if 157 is going to be done in summer school? No, it's not done anywhere. It's just there aren't enough students who take it. So first of all, this is a weird year. I have like 56 students still enrolled in 157. By this time, normally there's 20 students in 157. But you can imagine if you have 28 students in 157 during the main year, there's just not enough people who would take it in the summer to be offered. So unfortunately, yeah, it just doesn't end up being an option. That being said, if you want to take 137, which does a lot of very similar things, that is offered in the summer at St. George, Brandon. So if you want to check that out, you absolutely could. And if you take 137, yeah, sure. So if you want to become a math specialist, though, and especially if you choose to stay at UTM, you could take 137 and then you could come do 257 with me next year. And that is a usual thing. Like, that's not weird at all. And then once you have 257, it would basically unlock your ability to do other specialist stuff. And so you could totally do that. Mm-hmm. For the record, if you do that, you'll be the first ever 133 student to take that path. To my knowledge, ever. Yes. There have been a handful in history. There have only been one or two students from like 135, 136 who have done it. There has never been a 133 student who has ever done it, in my knowledge, of about the last 10 to 12 years at the University of Toronto, which isn't to like scare you or anything. I just want to, because most people who take 133 aren't necessarily hyper interested in math, or even if they are. So for example, any of you who know the TA Jordan, you know, Jordan likes math and he's pretty interested in it, but he also likes economics and finance. And so he didn't invest himself in a math specialist, right? And for him, it didn't make sense to take like 157 and 257, even though I think he would have done fine in it. And so the reason for that is not because it's too hard for a 133 student, right? That's not in any way the statement there. The issue is just that most students who take 133 aren't usually interested in doing math specialist degrees. So if you were to do that, you would, I think, be the first person ever. Okay, cool. Yeah, no, I mean, like, I'm happy to have done that. And I'm very excited to see how 102 works out for you. I think it'll be a very cool experience. But that being said, you're gonna have to work hard, right? 102 is a bit of a tricky course. It's tricky in part because I don't think it's well designed, but it's tricky as well because it'll be your first time doing proofs. So don't take it for granted, right? Just like make sure you work hard and stay on top of things and go to lots of office hours. And the moment you don't understand something, you know, talk to somebody, right? Ideally you should talk to a prof in that class, but if you come to these office hours and people aren't actively asking questions, ask me, right? Like, just don't let yourself fall behind in 102 because it's not a sympathetic course, right? It won't treat you nicely if you start to fall behind. Next week. So next week is expected value and conditional probability, which will not be on term test 3. And so then there's this very interesting question of whether or not we put it on term test 4, which I think we should because it's really important. That stuff is crazy important. But that would be the stuff that we do next week. And obviously that will also be the last week that we do stuff. Shanzai, no, this is an interesting question that I've always kind of thought about, because right now you've probably noticed we're doing a lot of discrete probability, right? Like we're doing, you know, things that aren't like the normal distribution, because the normal distribution is continuous, right? So we're doing a lot of discrete probability, but by the end of the course, we will actually have all the tools to do continuous probability, normal distributions, Poisson distributions, all those sorts of things, but they require integrals. So it's always something that I've been really interested in trying to figure out how to put into Math 133. But if I did that, I'd have to do integration much earlier into the course. And I'm not certain that that makes sense, that there's a way in which we could do it. It's totally fun. And the way that you compute probabilities, I think, are a lot even, there's a real sense in which I think it's a lot easier, even continuous probability distributions. But like I said, it's just a matter of the timing. I think on the other hand, if you plan on doing like econ, 220, I think 220 might do continuous probabilities. I'm hoping that they do. So you'd have an opportunity, I think, to do it there if you were to take that course. Alternatively, some of you, I think, have to take stats, right? Like actually stats 216 or 226 or something, like at some point in your course. No problem, Jack. See you later. So I think some of you actually have to take a stats course, and you probably would take it there, right? You'll see it there. But you know what? We can, yeah, exactly. And Shanze, if you want to talk about it, like once we do integrals, if you want to be like, hey, is this like, you know, how can we slot this into the normal distribution? I'm happy to talk to you about it then. You know, don't hesitate to ask extra questions beyond the course. I'm more than happy to answer those things. Yeah. But yeah, let's wait till we get to integrals first, which we'll probably do sometime in February. So in February, we'll be in a position where we have the tools to talk about those things. Okay, are we all good? Are all the questions answered? If so, we can call it 5 minutes early. Like I said, it's not a big deal. All right, I think we're done, right? I don't think anyone has any more questions. There's only a handful of us left. No more participant tests? Dodd, what do you mean by that? Like the bonus, right? Yeah, no, there's no more. Yeah, Ariana asked that, and yeah, no more of them. I know. But listen, you got 2%, right? 2% is pretty good. It's worth something. It's worth, you know what? If you did those quizzes, you can now miss 2 assignments and you would have gotten the same mark, right? So they're kind of free. They're freebies like that. I know. Students love the bonus stuff. We'll see, right? There's a couple things we could do. I think last year we did like an end of class survey that was worth an extra % as well. But we might do something like that. But there are no more of those like bonus quizzes planned, right? If something happens, it'd be kind of more towards the end of the course. No problem. Theodore, see you later. All right, everyone. I think 10% marks, except for which one? Yeah. I mean, what can I say? In math, sometimes you got to earn your marks, right? Like that's how it is here, except for 2%. The 2% you get the freebies. But I think I've tried to give it to you in different ways, right? I've tried to give you the 24-hour tests to make things a little bit easier that way, right? So sure, I didn't give you maybe that extra 8% for free, but there are other ways in which I've tried to make your lives a little bit easier, right? No problem, Christian. See you later. All right, everyone. I think we're going to sign off. Oh, thank you. Thank you, Dad. I appreciate that. Thank you, Curdy. I'll see you next week. Are you not coming on Thursday? You're going to be. See you, Brandon. Yeah, on Thursday. All right, everyone. Have a good Wednesday, and I'll see you in a couple days. Ciao.